everyone, my name is Saloni and today we'll discuss a question that will be helpful to you for all physics competitive exams. So thank you for watching this video. If you like our content, please subscribe to our channel to learn more about physics. Our next question says the two prominent wavelengths in the light emitted by hydrogen discharge are this and this. Okay, so basically there are two lambdas that has been given to us. One lambda is 6.56 nanometer, another lambda is equal to 486 nanometers. Light from a hydrogen lamp illuminates a diffraction grating with this. Okay, so we have 500 lines per millimeter. Okay, and the light is observed on a screen. So L is given as 1.5 meter behind the screen. What is the distance between first order red and blue fringes? Okay, so again we know that interference pattern for a diffraction grating is d sine theta m is equal to lambda and m is equal to 0, 1, 2, 3 and so on. Now we are given that there is 500 lines in 1 millimeter. Okay, so one line is in how many millimeters? It's 1 by 500. Okay, and what in SI unit you get when you convert into meter, you get 2 into 10 to the power 6 meters. So this is our D. So D came out as 2 into 10 to the power minus 6 meters. Okay. Now we have our D with us. Now if we use D sine theta m is lambda by D, right? So sine for first order maxima sine theta 1 is lambda. So from here theta 1 is sine inverse lambda D. For red, if we are talking about red fringe, then theta 1 is equal to sine inverse. If we take lambda then as of red color, then this is 656 into 10 to the power minus 9, because our wavelength of red color is 656 nanometers, and D is we calculated as 2 into 10 to the power minus 6. When you solve this thing, you get theta as this. Okay, now again you apply the same procedure for our blue light. So theta 1 for blue will be sine inverse 486 into 10 to the power minus 9 divided by 2 10 to the power minus 6. So theta 1 will come out as 14.06 degrees. Okay, for blue, for basically blue. But theta was 19.15. Now question, we can see we are asked what is the difference between first order red and blue fringes. Okay, so see, you can see from the angle that yeah, blue fringe will be, this is the screen and our first maximum of the blue fringe. This will be here and they will be here. So this is basically blue and this is red, first order maximum. Okay, now we have to calculate this distance. Okay, how you can calculate this distance? You know this distance. Can you calculate this distance? Yeah, if you know this angle, this is basically theta red and this one angle is theta 1 blue. This angle theta 1 red is equal to this y, this total y of red divided by this distance d, which is basically L. So y red divided by L. Okay, so simply, and in our question L is given as 1.5. So y of red will be L tan theta 1 red. Similarly, you can calculate this W. So this total is y of red. So from here, wait. So you have this y of red and this is y of blue. So the difference between this will be y of red minus y of blue. So y of blue I'll write as L theta 1 blue. Okay. And if you want to calculate delta y, delta y will be put L tan of red minus tan theta 1 of blue. So L is 1.5. This will be tan of 90.15 minus tan of 14.06. Okay. Delta y, when you calculate the whole thing, you get 0.145 meters, which is equal to 14.5 centimeters. This is our difference between those two first maximas, basically for two different colors. Okay. Our next question is, we're given there is a 500 line per millimeter diffraction gating. So simply from here you can calculate D, 10 to the power minus 3 divided by 500. Okay, you can calculate D. Lambda is given as, for D will be 2 into 10 to the power minus 6 meters, right? And lambda is given as 510 nanometers. How many bright fringes are seen on 2 millimeter wide screen located 2 millimeter? So this is, and the width of the screen is given as 2 meter. Okay. So from here, simply you have to calculate how many bright fringes will be there. Okay. So if you see the diagram, this is our diffraction grating, and if you imagine this as your screen, then definitely there is dark fringes, there's dark and there's dark, and then there is bright fringes, dark fringes, something like that. Okay, so and this width of the screen is given as 2 millimeters. Okay, so like we have this diffract interference factor, and this basically the width of the screen is given as 2 millimeters. Okay, so first of all what we'll do is we'll calculate m. We know that d sine theta is equal to m lambda. Okay, m is the order, so m is equal to d sine theta divided by lambda. And what this m will come, will from this will basically will round with m, and we'll just calculate our answer. Okay, so m is equal to d sine theta by lambda. Okay, and for what is m? M is the extreme, so this is our, like, for if you, right, so if this is the center, so this theta basically is the maximum theta, so the highest m for order, highest what order can be possible, this is the maximum theta. Okay, so first of all, m, from here we have m is equal to d sine theta divided by lambda. Now if this is the center, if this is y, what is this y? If this is 2 meter, y will be equal to 1 meter, of course. Right? Y is 1 meter. Okay. And from here you can write tan theta is equal to this 1 meter divided by this length. Okay. This length. This length is given as 2. Okay. This is also 2. Width is also 2, and this length, the space between slit and our screen is also 2. So tan theta is equal to 1 by 2. Okay. So from here m is equal to d into sine, this d by lambda, which is tan inverse 1 by 2. Okay, and so completely if you solve it, d basically is equal to 2 into 10 to the power minus 6, right? And lambda is 510 into 10 to the power minus 9 into sine tan inverse 1 by, okay. From when you solve this whole thing, your m will come out as 1.8. Okay, m will come out as 1.8. So see, if you see from this screen, okay, how can m be in, how can m be in decimal? So you have to m, you cannot take m greater than this, because then it requires a length of screen should be more for that, so you have to take one down. So for maximum, m should be equal to 1. So what will take, m is equal to 1. Okay, so what, how many bright fringes? So there'll be like, there'll be this there'll be center fringe, and there'll be m is equal to 1 fringe, and there'll be m is equal to this on both sides. So total fringes will be equal to 3. Okay, one is center and one is this one and this one both side. Total fringes will be equal to on this screen, on the size of the screen possible is 3. The next question says that there is a helium neon laser. The wavelength of the laser is 633 nanometers. Okay. It illuminates a single slit and observed on a screen 1.5 meter behind the slit. So L is given as 1.5 meters. Distance between the first and second max minima in the diffraction pattern is this. So the difference between first and second minima is 4.75 millimeters. What is the width in millimeters of the slit? So we have to calculate the width of the slit. So basically this is a diffraction pattern, right? This is our length of slit. Okay, and this is a screen, and you know how diffraction pattern comes. Center we have our maxima, and then yeah, maximum. It's saying that the first minima and the second minima basically, the first minima, this distance is basically 4.75 millimeters. So we know are basically the minima, these occurs at positions which is equal to y, p is equal to p, lambda l, yeah, lambda l by a. Okay. So for our first minima, it will be L lambda by A, and for our second minima, it will be 2L this. Okay, and you do delta Y is equal to Y2 minus Y1 is equal to 2 lambda L by A minus lambda L by A, which is lambda L by A. Okay, so from here, A will be lambda L by delta Y. Okay, and now you have to just put the values. So A is equal to lambda L by delta. Lambda is 633 nanometers. So 633 10 to the power minus 9 into L, which is 1.5 divided by 475 into 10 to the power minus 3. Okay, 10 to the power minus 3. And when you solve this whole thing, you get your answer as 2 into 10 to the power minus 4 meter, which is equal to 0.2 millimeters. So this is our answer. Okay. Next question says, calculate the transmission probability for a quantum mechanical tunneling in each of the following cases. First part is an electron with an energy deficient of U minus E is equal to this is incident on a square barrier potential of width this. Second is an electron with an energy deficient of 1 electron volt is incident on the same barrier. Third is an alpha particle whose mass is this with an energy deficient of 1 mega electron volt and incident on a square barrier of width 1 femtometer. And the D part is an 8 kg bowling ball with an energy deficient of 1 joule is incident on a square barrier of width 2 centimeters. So this is a 4-part question, and we'll solve each part individually. Okay. So first of all, we have to in this question we have to calculate the transmission probability for quantum tunneling. Okay. So we know the transmission probability coefficient for tunneling is e to the power minus 2cl. Okay, where c is under root 2m u minus e divided by h cut. Okay, where we know that mass m is in kilograms and u and e are in joules. Okay, so simply to compute c, first of all, you have to put the values. We are given that this energy deficient is 0.01 in electron volts. So you have to convert it into joules because everything we want to convert it into SI units, right? Divided by H cut we know is 1.055 into 10 to the power minus 34. So when you calculate this whole thing, it becomes 5.12 into 10 to the power 8 meter inverse. This is your C. If you have calculated C, then 2Cl would be equal to 2 into 5.12 into 10 to the power 8 into L. L is 0.1 into 10 to the power minus 9. Okay, so when you solve this thing, this is 0.1 102. So for first part, t is equal to uh, e to the power minus 2cl, which is equal to e to the power minus 0.102, which you solve, you get as 0.903. This is our t. Okay, our first part has been solved. For b part, c is equal to 2 into 9.11 into 10 to the power minus 31 into, we are given energy deficient as 1 electron volt. Again, if you want to convert it into joules, you have to multiply by 1.6 into 10 to the power minus 19 divided by 1.055 into 10 to the minus 34. So when you solve this, you get 5.12 into 10 to the power 9 meter inverse. Okay, so this is your C for second part. Okay, now for second part, you have to calculate T also. You have calculated C. Now T, uh, if you have calculated C, 2CL is equal to 2 into 5.12 into 10 to the power 9 into L is 0.1 into 10 to the power minus 9. So this comes as 1.02. So T for second part is equal to e to the power minus 1.02, which is 0.359. Okay. So this is for the second part. Third part, again, we have to calculate C for third part. For C is equal to 2 into mass. Okay. So for second part, see, for first part it was electron, but for third part, we given it's a alpha particle. So we're taking the mass different, which is 6.65 into 10 to the power minus 27 into, again, energy for this, they given 1 mega electron volt. So U minus E, basically the energy deficient U minus E is this, which is 1 into 10 to the power 6, because it's 1 mega electron volts, and now you have to convert 1 electron volt into joules. Okay, divided by H cut, which is 1.055 into 10 to the power minus 34. So C from here you can get as 4.37 into 10 to the power 14 meter inverse. Now you got C. To calculate 2CL, it is 2 into 4.37 into 10 to the power 14 into L is 1 into 10 to the power minus 15, which you get as 0.875. So T is equal to e to the power minus 2CL is equal to e to the power minus 0.875, which you get as 0.417. So this is our third part, tunneling, our transmission yet or tunneling probability for the C part. For the D part, which is an 8 kg bowling ball with energy deficient of 1 joule, is incident on a square barrier. Okay. See, this is a macroscopic particle. So from here only you should know the turning probability should be very less. But we'll calculate it. Okay. So 2CL for a D part is equal to 2 into C is 2 into the mass, which is 8, into U minus E, which is 1, divided by uh, not in the under root. So this divided by 1.055 into 10 to the power minus 34 into L. L is given as 0.02. Calculate this whole this thing, you get 1.52 into 10 to the power 33, and then T is equal to under root e to the power minus 2CL, which is minus 1 into 10 to the power 33. And when you get this whole thing, you get as, so see, this is very less. This is very less. So if you want to basically uh, get the idea of what this is, so what you can do is, it's e to the power minus 1.52 into 10 to the power 33 right? So if you want to get the idea of what this number is, what you can do is you can multiply by ln 10 and divide by ln 10. Okay, in the power only, do like this. Okay, and using the property of logarithms, you can write this as 10 to the power minus 6.59 into 10 to the power 32. Okay, because of course you can write this in the power, write this quantity in the power, and e to the power ln 10 is nothing but 10 only. So this is our answer. So this is, it's so like this is this quantity here, because it's minus, so it's actually this 10 to the power 6.59 into 10 to the power 32, right? So this thing, it's such a small quantity, so you can see that for how macroscopic particles, the tunneling probability is so low. So that's why you cannot move through walls, but microscopic particles can move through barriers. Okay, so next question says that an electron is an infinite deep potential well which has a ground state energy of this. Okay, so we are given that our ground state energy is this. So you can see that this is a two-part question. In the first part, we have to show that the photon emitted in a transition from n is equal to 3 state to n is equal to 1 state has this wavelength, which makes it green visible wavelength. So we have to prove that this is our lambda. And B is find the wavelength as a spectral region for which each of the 5 transitions that take place among the 4 lowest energy levels. Okay. So first of all, we have to show photon emitted in a transition from n is equal to 3 to n is equal to 2. Okay, and we're given that ground state energy is 0.3 and we're given infinite deep potential well. So we know that in infinite deep potential well, En is directly proportional to n square. So we'll use this thing here. Okay, so E1 for infinite deep potential, it starts with E1. So this is, suppose we are given that the ground state is 0.3, so 0.3 electron volt. Okay, so for E2 we know it will be 2 square into 0.3, which will be equal to 1.2 electron volt. Similarly for E3 it will be 3 square into 0.3, which will be equal to 2.7 electron volt, and for E4 it will be 4 square into 0.3, which will be equal to 4.8 electron volt. Okay, so we have calculated all the 4 levels. Okay, we have to show from n is equal to 3 to n is equal to 4. So for n is equal to, if there is a transition from n is equal to 3 to n is equal to 4, this is the energy that comes out in terms of a photon. So this is 2.7 minus 0.3, which is equal to 2.4 electron volt. Now from here we know that lambda will be equal to hc by E. Okay, using E is equal to hf. Okay, so lambda will be equal to, we know hc in terms of electron volt nanometer is this 1240 electron volt nanometer divided by the energy, which is 2.4 electron volt. So you calculate this, you get 517 nanometer. This was what was required in the first part, and it is in the green light region. Okay. Okay, so this is for part A. For second part, find the wavelength spectral region for each of the 5 transitions that take place among the 4 lowest energy levels. Okay, so that's why we calculated the 4 energy levels. Now we'll find this. We'll find in what spectral region they lie. Okay, so first of all, let's transit from E2 to E1. Okay, from second, see we have 1 2 3 4, so from second to first. Okay, so this is from E2 minus, we'll do E2 minus E1, which will be equal to 1.2 minus 0.3, which is equal to 0.9 electron volt. Similarly as we did in the first part, we'll write by delta E. Okay, so this will be equal to 1240 electron volt nanometer divided by 0.9 electron volt, which will be equal to 1.38 nanometer, which is equal to 1.3 micrometer. Okay. Uh, Sorry, this is this is 1380 nanometer, which comes as 1.38 micrometer. Okay. So this is our lambda here, and so this particular lambda, that is 1.3 micrometer, this lies in the range infrared. Okay, this is the infrared range. Okay, similarly, you can go from, we have 1 2 3 4, 1 2 3 4. So we did this. Now if we calculate from 3 to 2, our delta E will be equal to 1.5, and when you apply the same formula, you get 827 nanometer, which is in infrared region. Okay, similarly, this is the second transition we take. Third transition, if you take from 4 to 1, let's say you take from 4 to 1, so lambda will be equal to, uh, here E will be, delta E will be equal to 4.5 electron volt. So our lambda will come as 275 nanometer, which is an ultraviolet range. Okay, also other transitions that you can take is from 4 to 2. Okay, so we have taken 2 to 1, we have taken 3 to 2. Okay, initially we discussed, uh, we have already discussed 3 to 1 transition in part A. So basically that's why we're discussing 2 to 1, 3 to 2, then 4 to 1, 4 to 1, 4 to 2, and 4 to 3. Okay, so we have calculated 4 to 1. Now we calculate 4 to 2. That is, delta E comes at 3.6 electron volt, and lambda comes as 344 nanometer, which is in, again, ultraviolet range. And now 4 to 3, if we go, delta E is equal to 2.1 electron volt. So lambda comes as 590 nanometer, which is yellow orange light, and it's basically visible range. Okay, so this is how you solve these kind of questions.